So hi guys,
So hi guys, we'll be starting the session in few minutes, like 2 to 3 minutes. Yeah, yes, we are starting now. So thank you guys for joining for this session, and thank you Dhanya for the amazing theory session. So I'll share my screen now. Is my screen visible?
Yes, yes.
Okay, we'll start with the numericals. So before getting in, like we had a theory session now about pipelining. The main aim of the pipelining is we have a lot of instructions and we have to execute it. So, in what way we can minimize the time for its execution is the main aim of pipelining. So, before getting into the numericals, let's just revise the formulas. So, we'll consider this n as number of instructions to be done or to be executed. K will be the number of stages. The small t will be the time for the execution of a single stage, and t will be the total time to complete all the tasks. For pipeline and non-pipelining, it depends. So when we have four formulas for pipelining mainly. So the first case will be when the time for all the stages are equal. That is, all the stages in to be executed will be executed in the same time. So in that case, for without pipelining, we have the total time is equals to n into k into t, which is the total number of instructions into the number of stages into the time of each stage, which is set as n into k clock cycles. And the second will be with pipelining, that is equals to t is equal to k plus n minus 1 into t. And the reason for all these is what we saw in the theory session. And when the time is different for all the stages, in the case of without pipelining, it will be n into the sum of the time of all the stages. That is, for example, if the time of the stages are 10, 20, and 30, the total sum is 60 into the number of instructions, which gives the total time of without pipelining. And in the case of with pipelining, t is equals to sum of time of all the stages plus n minus 1 into time of the slower stage. So in this case, only the first instruction takes the overall time and the subsequent instructions just take the time of the slower stage. So that is what they say the slower stage determines the overall time of the pipeline. So these are the main formulas of pipelining. And other formulas are speed up is equals to time of non-pipeline divided by the time of total pipeline form. So next will be the efficiency of utilization, which is the speed up by K, which gives the efficiency of this whole system. And frequency is also known as clock rate, which is equals to 1 by time of the slow stage, which is usually said as the clock rate of the pipeline system. and the time is considered to be the slow stage here. So it is also generally said that speed up will be approximately or must be equal to the number of stages frequency. Next is latency. Latency is time to complete all the stages for a single task. So the main motive of pipelining is that it preserves the latency of all the tasks but increases the overall throughput. So what is latency in the sense? The time to complete a single instruction is always preserved if we see individually. But as overall throughput, the overall time will be reduced. And what is the throughput? We also have a formula for it, which is equal to number of instructions by total time taken. So these are the overall formulas which we have in this chapter. So if you guys want, I'll also send it in the group as well. Next, going into some basic concepts. So this is a two-stage pipeline, and this is a normal way and this is a pipelined way, which makes the system to work faster. And this will be a three-stage pipeline, which also works in the same way. And just like in the washing machine example, we have three different stages. In a normal instruction or in COA standards, we'll be having five different stages, and we'll work mainly on four stages, which is fetch, decode, execute, and write back. So regarding the hazards, there are three types of hazards: structural, data, and control, which we saw in the theory session as well. You can just read this if you want. Clock cycles, find the time for non-pipeline and pipeline cycles, and put your answers in the chat box. Guys, anybody want to answer? Okay, then I we'll see the answer how it goes. So first, you have to they are asked for the time of non-pipeline. So since the time is same for all the clock cycles, the formula would be n into k into t, where n will be 8 into 5, which is 40 clock cycles. So n will be 8 into 5, which is 40 clock cycles. Then how about pipeline? So pipeline has the formula n plus k minus 1 into t, where the k will be 5 and n minus 1 would be 7 into t, which is actually 12t 12 T clock cycles and 40 T clock cycles. Okay. And now we have the T equals to 3 by 12T, that is equals to 3.33. And now they've also asked for efficiency. Efficiency is equals to speed up by k, that is 3.33 divided by 5, that is 0.6666. And the pipeline system is just said to be 66% more efficient than non-pipeline. And at last, they have asked the throughput. Throughput is simply the total number of instructions by total time taken for the pipeline system, which is actually 8 by 12T is equals to 0.66 by T. And if we calculate the throughput of the non-pipeline, we get it as 0.2 by T. Hence, we conclude that the overall throughput of pipeline is more than the overall throughput of the non-pipeline system. So, solving this sum gives you the basic idea of all the parameters involved in the pipeline. Now, we are getting into the first gate question. Consider a 5-stage pipeline with a cycle time of 5 nanoseconds. Calculate the execution time of 100 instructions and speed up due to the pipeline, and also find the utilization. So we have k is equals to 5 and the cycle time of 5 nanoseconds. Calculate the execution time of 100 instructions and speed up due to the pipeline. So we also have n is equals to 100. So the total time for the pipe, just a minute, for pipeline has the formula k plus minus 1 into t. So on substituting the values, we have 5 plus 99 into 5 nanoseconds, which gives me the answer as uh, 520 nanoseconds as well. So since they have asked for the speed up too, we need to find the time of non-pipelining case as well. So what is the formula for non-pipelining? And by following the formula, we'll be getting as 500, 500 into 5 nanoseconds. What is the speed up? Speed up would be 2500 divided by 520, right? And thus we'll get the answer as around 4.80, which is approximately equal to the k value here. So as we increase the number of instructions, we will be able to attain this approximation. And finally, they have asked for utilization. Utilization is also known as efficiency. So what is the formula for efficiency? And by solving the value, we'll be getting it as 4.8 by 5, which is equals to 0.9615. So the overall answers for this problem will be the time for execution time of 100 instructions for pipelining would be 520 nanoseconds. For non-pipelining would be 2500 nanoseconds. The speed up will be 4.8 and efficiency would be 0.9615. Moving on to next question. Consider a 5-stage pipeline with delay of each stage given by different times. So here each stage is having different time respectively. So calculate the execution of 100 instructions and the speed of the pipeline. So in the case of different times, we have different formulas for both pipelining and non-pipelining. So first, pipelining would be the sum of all the stages plus n minus 1 into time of the slow stage. So sum of all the stages would give me 63 plus n minus 1 would be 99 into the slow stage here is 16. So it is 16. So what is the total time now? It will be 63 plus 99 into 16, which gives me 1647 nanoseconds in the case of pipeline. Now since they have asked for the speed up similar to the last sum, we'll be finding the time which is taken for non-pipeline case as well. And for that, we have the formula n into the overall time, that is the total time taken for each instruction, and that will be 100 into 63 here. Seconds. And now finding up for the speed up, this will be 6300 divided by 1647, which is approximately equals to 3.8, 3.82. So the answer for this question would be 3.82, which is the speed up which they have asked. So the catch here is that all the stages are different, have different time. So we have to solve it accordingly with the different formula. Okay, so now we'll solve this sum, where this is the gate sum in computer science paper of 2011. Consider an instruction pipeline. The pipeline registers are required between. For the pipeline registers are given in the figure. Okay, so there are 4 stages here, and in between each stage there is a delay register, which is the time taken to take the value from this stage and put it here. What is the approximate speed up of the pipeline in steady state and under ideal conditions compared to the corresponding non-pipeline implementation? So we have case equals to 4 and instructions we take it as 100 and the time of individual stages is given. So the main role of delay registers is that they'll be considered only for pipelining. So this delay usually occurs in the case of pipelining when we have need to take the value from one stage to the next stage. And these delays usually not occur in a non-pipelining stage. So we'll be considering these delays only in pipelining values which are going to take. So since they have asked for the time for pipelining, and since the individual delays are given, we'll use that formula. So the sum of all the stages, that is 5 plus 6 plus 11 plus 8, and also we need to include the delays as well. So sum of all these plus 4 would give me just a second 30. So this gives me 30 plus the instructions were taking it as 100. So that will be 34 plus 99 into 12. Why 12? Because that is the slower stage which we need to take, and it is 11. And we also need to include the 1 nanoseconds, which is the delay caused because of this stage. So here the answer would be 1222 nanoseconds. And then we'll be solving for non-pipeline case, which is equals to just n into the total time which is being taken. And here we won't include the 1 nanoseconds delay since it is a non-pipeline case, so we take it as 30, which is equals to 3000 nanoseconds. So finally, speed up is equal to 2.455. So finding the time for pipeline and finding the time for non-pipeline case matters here. Finding speed up is somewhat easy. So hope you guys understood this sum. So any doubts till now in any of the sums which we solved? Okay, thanks for the reply. Moving on to this sum. Consider a 5 stage operations, and if the buffer delay is 20 nanoseconds, calculate the speed up of the pipeline processor, then n is equal to 100. So this sum is also similar to the previous sum. So I'll just solve it quickly. So but here the overall buffer delay is given, so we need to solve it accordingly. So the time of pipeline will be 200 plus n minus 1 instructions into 100, and then the time of non-pipeline would be the total number of instructions into the total sum of all the individual times, which I get it as 100. Just a minute. And finally, the speed up. It is simply the time of non-pipeline divided by the type of pipeline, which I would approximately get my answer as 1.98, approximately equal to 2. So this is also a simple question. So we have to know how to work with this buffer delay, and thus we are able to solve this sum easily. Next, we are moving on to this sum, which is a two pipeline sum. Assume we have two pipelines, P1 and P2, respectively. P1 has 6 stages, having execution time of 12, 14, 19, 20, time of 10 nanoseconds. Calculate the time that can be saved by using P2 pipeline over P1 pipeline if 2000 instructions are executed. So here we have two pipelines, which is P1 and P2, where the number of stages is 6 and n is equals to 2000. But in P1, the times are different for each stage, while in P2, k is equals to 4, n is equals to 2000, and time will be 10 nanoseconds. So basically, we need to find P1 minus P2 to find how much P2 is more than P1. So first, we are having P1, and since both are pipeline, there is not necessary to find the time for non-pipeline case. So we only find the time for pipeline, and the first case, since all the times are different, we'll be using that formula where it is actually the into the time of the slowest time. So on adding all the individual time values, we'll be getting 112 plus n is actually 2000, so n minus 1 will be 199 into the slowest time. The slowest time will be 25. So this is 25. So what does this give? This gives around 15087 nanoseconds. So the time for pipeline is, for the case of P1, is 50087 nanoseconds. Now similarly we need to find for P2 using the formula for that one. So the formula for this would be n plus 1 minus k into t. So what is n? N would be 2000, n minus 1 would be 1999 plus k. K would be 4. So on calculating this, I would get 20030 nanoseconds. So that's it. So what is the time difference? Like how much time will be saved by using P2 over P1? That is found by simply subtracting P1 minus P2, which is 50087 minus 20030, which is around nanoseconds, which we can also say it as 30 microseconds as well. So this sum is also somewhat easy to be solved. So like get questions, the questions seem to be big, but the answers seem to be simple. Till the questions we saw till now. Moving on to this question, assume a pipeline P which operates at 3 gigahertz clock rate. It has a speed up factor of 10 and efficiency of 40%. Calculate the number of stages in above pipeline. So here we have the speed up and efficiency is 40% and the clock frequency is 3 gigahertz. You have to find K. So efficiency is 40% can be written as efficiency equal to 0.4 than the previous one. So just by recalling the would be the time of non-pipeline by time of pipeline. While in the case of efficiency, it is speed up by K. So the formula for efficiency is equals to speed up by K. So once we get this formula, then it is almost easy to solve. K is equals to speed up by efficiency. And thus on solving this, what is the speed up? Speed up is 10 divided by efficiency is 0.4. And that gives me the value of 25. So for this pipeline to be achieved, the number of stages should be 25. To make my pipeline work with these conditions of speed up is 10, efficiency 40, and clock frequency of 3 gigahertz. Next, moving on to last three questions. Like these questions will be comparatively difficult. Consider a non-pipeline processor with a clock rate of 2.5 gigahertz and average cycles per instruction of 4. The same processor is upgraded to a pipeline processor with 5 stages. But due to internal pipeline delay, the clock speed is reduced to 2 gigahertz. Assume that there are no stalls in the pipeline. The speed up achieved in this pipeline processor is. Okay, so we have in the non-pipeline case, we have the clock rate is equal to 2.5 gigahertz and the cycles per instruction is 4. In the case of pipeline, we'll be having K is equals to 5 and clock rate is equals to 2 gigahertz and N is equals to 100. So for basically the frequency, or it is simply said as 1 by the clock cycle time. What is clock cycle time? Clock cycle time for a pipeline system is the time which is taken for a slower step to happen. So the clock rate is simply the 1 by clock cycle time, that is 1 by time of the slower step. So since we have the clock rate of both the cases here, we need to find the clock cycle time for both the cases. So I'll shortly put it as CCT for non-pipeline case would be 2.5 GB, which would give me we'll be getting the individual time for these both the cases. which is actually equal to the small t which we'll be using in those formula. CCT of pipeline which is equals to 1 by it is reduced to 2 gigahertz and I'll be getting 0.5 nanoseconds. And that's the time for both the cases we found. Now, in order to get the speed up, it is necessary to find the total time and divide them to find the speed up. So, in the case of so the number of cycles which takes to implement a single instruction, which for a single instruction is said to be n into k. But in the case of here it is 100 instructions, so we'll be consider it as a k value. So n in k into what is the time value for non-pipeline? It would be 0.4. In total, we'll be getting it as 160 nanoseconds since this is in nanoseconds as well. Yes. And next, moving on to pipeline systems. Since the time is same for all, we have this formula n plus k minus 1 into t, which will be 100 minus 1 plus 5, which is 104 into the time that would be 0.5, which is equals to 52 nanoseconds. Thus, for the speed up, it is just 160 divided by 52, that is 3.07. So the speed up of this the pipeline processor would be 3.07. Hope you guys understood this problem. So converting this clock rate into the time and just substituting are the main thing which has to be done. This is the 2015 gate question. Now moving on to this question, and I want you guys to answer this. It is the easy one. Consider the following process. Assume that the pipeline registers have zero latency. Pipeline 1, 4-stage pipeline with these timings. 4-stage pipeline with these timings P2, P3 with these, and P4 with these. Which processor has the highest peak clock frequency? Can any of you guys put it in the chat box? Yes, it's actually P3. Thank you, Harish, for your answer. So since they have asked for highest peak clock frequency, hello, chat. Yes. Yeah, just we'll complete this question. So since they have asked for the highest peak clock frequency, we'll just take the slowest time of all these phases. So P1 will be 2 nanoseconds, P2 will be 1.5 nanoseconds, P3 will be 1 nanosecond, and P4 will be 1.1 nanoseconds. So in order to find peak frequency, we need to find the lowest clock since they both are inversely proportional. So in this case, we'll be having P3 as the lowest time, and this gives us the highest peak clock frequency. So the answer for this would be P3. And we just have one final question, which we'll be solving in the next session. That you guys. Thank you. So a non-pipeline processor takes 50 nanoseconds to execute one instruction. The same processor is converted into a 5-stage pipeline, with stage delays as follows. And next, pipeline register overhead is 2 nanoseconds per stage. Due to hazards, 20% of instructions cost one stall cycle, 10% of instructions cost two stall cycles. For a program of 100 instructions, find clock cycle time, total execution pipeline, and speed up over the non-pipeline processor. So first, getting into the clock cycle time. So as we discussed before, the clock cycle time is simply the time of the slower stage of the pipeline processor. So here in this case, it is 12 nanoseconds, and also there is a delay of 2 nanoseconds per stage. So we need to include this as well. So 12 plus 2, the clock cycle time would be 14 nanoseconds. And this is the answer for the first part of the question. Moving on to next, total execution time for pipeline. So since all the times are different here, we'll be using the sum of all stages into n minus 1 into the time of the slower stage. The sum of all these stages would be 8 plus 10 plus 12 plus 9 plus 11, and that would give me 30 time, time of pipeline. And the sum of all these would give me 30, but we also need to include the 2ns per stage. So 2 into 5, that also gives me 10. So the total time would be 40 for a single instruction plus 99 into the time of the slower stage or the clock cycle time we can say, which is 14 nanoseconds. Hope you guys understood this step. Just a minute, this might be confusing. And this would give me the answer as 1426 nanoseconds. So the total time for pipelining would be this, but we also have some hazards to be solved in this case. So we should also include that one in this case as well. Just a minute. So in the case of hazards, we are able to see 20% of instructions causes one stall cycle, and 10% of instructions cause two stall cycles. So 20% of 100 would be 20. So 20 instructions is said to cause one stall cycle is extra. So stall cycle in the sense, in this case, it is just 14 nanoseconds. So with the time which we already have, we need to also include the time which is caused due to hazards. Since 20 instructions are causing a one stall cycle, we need to add these 20 into 14 nanoseconds to this to time. So these 20 instructions, each of them cause one stall cycle. And since each of them cause one stall cycle, we'll be multiplying 14 nanoseconds for each clock cycle which is causing this hazard. And this time will be added to the total time which we have till now. So similarly, we also have 10% of 100 instructions, which is set to cause two stall cycles. So this is 10 into 14 into 2 stall cycles, which is equals to 280 nanoseconds here, and this also equals to 280 nanoseconds. So the total time for the pipeline processor will be sum of all these three, which is equals to 1426 plus 560, which is in total equal to 1986 nanoseconds. So the total time for pipeline would be 1986 nanoseconds, and we have also included the hazards time as well. Now, since they have asked for speed up, we need to calculate the time of the non-pipeline processor. And for this, we need to use the first line of the question. The time of this non-pipeline for different times would be n into the total time, which is this one. What is n? N would here we should not include this delay time. Only pipeline one, and sum of this would be 30, which is equals to 3000 nanoseconds. So finally, for speed up, it is simply 3000 divided by 1986, where we'll be getting the answer around 2.51. That's it. So the main thing is here is that we need to include these hazards also to the time which is involved for pipelining, and then I guess other things would be easy. So that's it, guys. We have solved most of the gate questions from this unit. So I guess it won't be more difficult than these questions. So I'll send this doc. You guys refer it. I send this docs in the group. You guys can also see it there. So any doubts you can ask me or Dhanya in the group or individual as well. Any doubts till now you guys got? Okay then. I think we can end the meeting. Dhanya, do you have anything to? Okay then, guys. Thank you
Thank
all
you
for
everyone for
joining.
joining.
Thank you all for joining, guys.